Do the first math of a long journey of mathematics of neural network. All right. But before I do that, I want to revise a little bit a problem that we studied in class last time, which was the regression problem. You guys remember this picture? The idea was, if you're given a bunch of data, which are the blue dots here on the picture, can you draw a line of best fit? It's a standard classical regression problem. What we saw in the previous lecture was, can I draw the line of best fit by starting from a random position and employing my stochastic gradient descent or the incremental gradient descent and updating my line of fit that basically translates to minimizing my loss, and the loss was the sum of squared errors. Okay, so the red line is the random model with the model weights M and C, if you recall. Let me redo the math a little bit. You have a set of data points, x1, y1, x2, y2, all the way up to xn, yn. Okay, so these are all the blue dots, x on the horizontal axis, y on the vertical axis. And our objective is to draw a line of best fit, what we call the linear regression model of the data. Now, since this is a line, that model, which we call capital M, takes in the input x and spits out a y, but it is parameterized by two parameters which we denoted in vectorial form in terms of alpha. So this is y mx plus c. So alpha is a stack comprising m and c, the slope and the y-intercept, and we want to find that value of m and that value of c that defines the line of best fit that passes through the data points. And how did we proceed? We said, well, we are going to do that in terms of minimizing the sum of square errors. So I have n data points, so I run over my sum, run my sum over all the data points, and I have the values of the data points yi. Then this is my predicted value of yi. This is my yi hat predicted. They may or may not be same, because after all it's a model, and we square this deviation and we want to minimize this, right? This is what we call the loss function, which was a function of m and c. You can think of the m and c in some abstract sense to be the weights, because our lecture today is about neural networks, so it's good that we start thinking in terms of weights. So essentially these are the weights that you want to update. So the stochastic update is follows: the I plus 1th iterate, you update the values of m and c based on what your values of m and c were at the ith update, minus some learning rate. This is the learning rate. Always positive. Gradient of some data point k of f. Remember, this is where we saw the difference between the stochastic gradient descent and the full gradient descent, or the batch gradient descent. The batch gradient descent, I wouldn't write that k, because I would take the gradient of this expression with the sum intact. But I want to do things fast, so I won't worry about the summation. I'll take the gradient of a randomly selected data point, and that's my k of mc. So this is a vector, okay, del f, del m, del f, del c at the ith instant of the weights. And I keep doing that until I hit a stopping criteria, which could be, both the derivatives in the gradient almost equal to 0, and you can put a tolerance to define what almost means. And when we run that in a computer, this is what it does, right? It updates the red line, the line of best fit, and slowly this thing settles here. And we have kind of minimized the loss here, and we say this is the line of best fit with the weights corresponding to whatever the weights, the slope of the line and the intercept of that line is. This is a linear regression model, and we have employed the stochastic gradient descent. Very simple idea. It's a very simple problem, but a very widely used problem in data science. Today, we will study the same problem, but instead of taking the model as m alpha x, which is y equals mx plus c, instead of taking this as our model, we will take the deep neural network model. And since this is your first introduction to neural network, we will not dig deep, we'll just scratch the top. But I'll show you the math. Okay, so instead of the line of best fit model, which is y equals mx plus c, which is what is went in when we define the loss function, we will use the deep neural network. And like I said, because it's your first introduction, we'll scratch the top and we'll do some math and show you the mathematics, and hopefully leave you with enough room for imagination so that you can go and start dreaming about the deep neural network. Okay? So does everyone understand the difference between what I have shown in the previous class and what I propose to show today? It's the same problem, the same application. What application is it? It is the application of linear regression. Regression, essentially. I'm going to find a regression model to draw a line of best fit or a curve of best fit through the data. That's the objective. But I'll employ a different model. So I can employ any model to define my data. All right. So, because as some of you were saying, you have seen what the neural network looks like, let me actually ask you a question. See if you've understood the animation that you've seen in the AI class. You see this data here? Does everyone see the data? Yeah, the blue dots. What is the input and what is the output? X is the input, Y is the output. Okay. What is the dimension of the input? Dimension of the input. 1. Why? But there are so many dots. But what about all those many dots? Why do you say there is only one X? The answer is correct, but I want to make sure that you fully understood when you say dimension is 1. What you see, the plurality of the red dots corresponds to the number of samples. So you have n samples but one-dimensional data. Multiple one-dimensional input points. Is that clear to everyone? All right. So D equal to 1 input dimension. What is the output dimension? 1. Good. Now, in terms of the picture of the neurons that you have seen, can you tell me how many neurons are there at the very first layer? Why? Well, है तो n samples ना? All those input points. So there is only one gola, like he said. Is that the terminology they used in the AI class? The gola. This is the input gola. Okay. How many output golas are there? How many output golas? Also 1. After all, m alpha x is exactly that. एक x का, एक y hat. Right? So the input and output golas are 1 neurons. Let's say we have only one hidden layer. You could have multiple hidden layers. Right? This is a hidden layer here, there's a hidden layer here, there's a hidden layer here. Each hidden layer can have multiple neurons. And this is the picture most likely that you have seen. And all these weights going here. Right? No, I'm not drawing all of them, but and some of them are lighted up, some of them are not lighted up, depending upon what is your dropout and all that. So you might have seen this animation. If you have not seen that in the AI class, in case you were absent, you might have seen it on your LinkedIn feed or your YouTube or whatever it is that you guys watch. Right? And each of these edges are your weights. Could be W1, W2, W3, so many of them. And then each neuron has a bias, set of bias, right? So one bias for every neuron. Another bias here. These weights and biases induce what is known as the induced field, which is the values, the numerical values of each of these neurons. And they get multiplied by the weight, added by the bias. And then what you have is the activation function. Because just because you have numerical values inside the neuron doesn't mean that you would like it to fire. Just like the biological neurons in your body. Not every biological neuron is firing all the time. It is firing only if a certain threshold is exceeded. So if you have an induced field, which is the product of some weight feeding into it, plus some bias, and this is some numerical number, you may not want it to fire. So you could have, any questions? You could have a Heaviside function saying that only if this number is above something, then I will assign the value 1. Let's call this entire thing as z. If z is greater than some threshold, otherwise if z is less than or equal to some threshold, I'm going to set it to 0. This is one activation function, need not be the only activation function. You mentioned the sigmoid activation function. The sigmoid activation function has the form 1 divided by 1 plus e to the negative z. And this has a range from 0 to 1. So these are, perfectly suitable to encompass probabilistic outcomes. So at every neuron, you have the induced field, which are the numerical entries. But the numerical entries become important, or the neurons fire, if the activation function, when it acts upon those neurons, if it gives you a value which is big enough, then it fires. If it's small enough, then it doesn't fire. In fact, the sigmoid function looks something like this. And no wonder you would want it to look something like this. If a certain threshold is exceeded, it is, firing. This is, let's say, the threshold. Otherwise, the value is there. This is very smooth, differentiable, and you'll see why differentiability is important here when I discuss the backpropagation. So this is largely speaking what happens at every layer. And finally, you have an output, and that's your y hat. All right? Is that pretty much the picture that you sensed from? Okay, good. Now, we want to do the math of all this and then implement it in Python using the stochastic gradient descent to see how this neural network model works. All right. Now, because this is your first introduction, mathematical introduction to this discussion, I will start with one hidden layer. Okay, one hidden layer. So I have one input ka gola and one output gola. So output, this is input, and only one hidden layer. And for most part of the discussion, that hidden layer will have only one neuron. Very, very simple model. And then I'll show you towards the end what happens when you have multiple neurons. But this is the hidden layer. Okay? So what happens is you have an X, there is a weight W1. Okay? This is Xi because I'm talking about the ith data point. There's W1, the weight, which multiplies with this Xi, and there is a bias B1. So this Z1 here is, let me just say Zi, because it's implied is the first hidden layer, because there's only one hidden layer. Zi, because it corresponds to the ith data point, is W1 Xi plus B1. But remember, whatever this value of Zi is, I do not immediately feed that to the output neuron. There is something else that I do before that. What is that? Activation. So I'll have another kind of imaginary thing, which is the activated. Well, actually, I should not draw the activation function inside the neuron. Probably draw it on the edge. This is the activation function, and this is HI, and in this case we will take the sigmoid activation function. So sigmoid of Zi, this is Zi, and whatever that value of HI is, which is sigmoid of Zi, I will feed with another weight to my output, but before that I need to add a bias. So this is my output. This is yi hat, which is W2 HI plus B2. This Wi hat is exactly this Wi hat in the regression problem, and that's my predicted value of yi corresponding to the input xi. Is that setup clear to everyone? Any questions? Any questions? No? All right. This entire calculation is what we call the forward pass. Picking up the xi, multiplying by W1 plus BI, computing Zi, then the activation function, feed to the output neuron, multiplied by W2 plus B2, and that output. That entire process is what is known as the forward pass of the neural network implementation. Now, I have my yi hat. I hope it to be good, and I hope that it matches very well with my yi. But that need not be the case at the first attempt. Okay, I might incur loss, and in fact, in most problems, you will incur loss or an error. So my error is yi minus yi hat. And my loss is, like I defined there, yi minus yi hat whole square. And if I'm talking about the mean squared error loss, if I choose that, then I'll have a normalization with n data points, sum over I equals 1 to n. But because we have chosen the stochastic gradient descent, I will not worry about the 1 over n and the summation. This is the loss function that I will work with. My loss function is like my f. In fact, my f was my loss function. This is my ith loss. This is equivalent to my fi. Here, I had m and c as my weights or arguments to the loss function. Here, what are the arguments to the loss function? These are the model parameters. What are the model parameters? W1, B1, W2, B2. So there are 4 of them as opposed to 2 here. They're the biases, right? So how many derivatives will the gradient of the loss have? 4. 1 corresponding to each of the weight or the bias. All right. So my gradient of loss for the ith data point will be a stack of 4 partial derivatives. Okay. So I'll have to compute each of these derivatives. How do I compute them? So I'll have to keep that picture in mind. I have to keep this picture in mind, the picture of the neural network. All right? And I have to compute these derivatives. In fact, why did I write f? Let me just write loss to make things more explicit. F is my loss, but I'll be explicit. And I hope you understand why I am writing the subscript I. Because this is stochastic gradient descent, I'm talking about the ith randomly chosen data point at every epoch. Okay, there are 4 of them. Which one do you think you should compute first? Which of these 4 derivatives do you think you should compute first? Or would it make sense to compute first? From stepwise? Which step? Which one? The first one? But where is the loss being incurred? At the very end. So it might make sense to compute what is closer to the loss. Okay? So let's compute this first. Del F, which is del loss I over del W2. Well, this is chain rule from calculus. You see, calculus doesn't go away, linear algebra doesn't go away, probability and statistics do not go away. 3 very important topics along with optimization. So chain rule from calculus tells me derivative of loss I with respect to yi hat, because that's what I have. My output, the predicted value, and my W2 appears in the expression for yi hat. So I apply the chain rule with respect to yi hat. Then derivative of yi hat with respect to W2. All right? So what is dy hat del W2? That's hi. And what is d loss I with respect to dy hat? It's from here 2 times yi minus yi hat, but there is a negative here, so negative 2 times hi. That's my third component of the gradient. What about this guy? I'll do the same thing. D loss I, dB2. I'll first do the differentiation with respect to dy hat, because that's what I have actually. That's my output, predicted output. That's what I have. So better differentiate with respect to that. Times dy hat dB2. dy hat dB2 is what? Look at the model. 1. So I'm left with just this entity here, which is negative 2 yi minus yi hat. That's my fourth entity in my gradient stack. Okay? I'm done with the output layer. So I can now afford to go further back from the loss. Okay? Because the loss should carry all the way, all the information from the loss should carry all the way to the input. That's the whole objective. So I'm done with the output layer. Now here the hidden layer. So this is my first calculation of the gradient. The second entity, let's do here maybe. How much time do we have? Hmm? 17 minutes? D loss I dW1. Okay. Yeah. So how do you think we will compute this? Well, what do I have? I have my yi hat. That's what I have, right? So let's start with that. D loss I, d yi hat. Again, remember, I'm applying the chain rule. Then I have an expression that connects yi hat and hi. So my next differentiation better be with respect to hi. So d yi hat d hi. Okay. My hi is expressed or expresses zi. So the next differentiation is with respect to zi. And my zi expresses W1. Why? Because Zi is W1xi plus B1. Okay? All right. Let's see what each of these derivatives are. So what is dzi del wi? That's xi. What is dhi dzi? Let's remind ourselves, what is hi? Hi is sigmoid zi. Okay? Sigmoid zi is 1 over 1 plus e to the negative zi. That's the definition of the sigmoid function. So if I take the derivative with respect to zi, then how would I differentiate this? I'll apply the chain rule. Derivative of this term, which is negative 1 over 1 plus e to the negative zi whole square, times the derivative of the denominator, which is negative. The negative and negative become positive, e to the negative zi. Can I write this expression in terms of hi itself? Huh? How can I write that? Well, let's compute 1 minus hi. Let's see what that is. So 1 minus 1 over 1 plus e to the negative zi is 1 plus e to the negative zi. I have e to the negative zi. Okay? So I have one piece, this, and one piece which is 1 plus e to the negative zi. That is exactly this expression. So 1 minus hi times hi is the derivative of hi. Okay? Basic calculus of one variable. This is hi times 1 minus hi. What about the derivative of yi hat with respect to hi? That's w2. But hey, great, I know w2 because it was defined earlier. I'm going in the reverse direction. And then, of course, I have what is derivative of loci yi hat because I computed it there somewhere here. So that's negative 2 yi minus yi hat. The product of these terms. That's my third entity, or in fact the first entity in my gradient stack. Now I'm left with d loci db1. That shouldn't be that difficult. It is exactly this. Loci dyi hat, dyi hat, dhi, hi, dzi, dzi, db1. This term is 1, everything else stays the same. Negative 2 yi minus yi hat w2 h2 hi 1 minus hi. So that's how all the entities of the gradient of the loss function is defined. Once you have the gradients of the loss function, then you can use it in the stochastic gradient descent update, just like here. Here we had m and c. Instead of m and c, we now have 4 entities: w1i, b1i, w2i, b2i. This is I plus 1. These are w1i, b1i, w2i, and b2i minus eta times these guys. This all this 4 I'm not going to write the expressions again. I'm going to write 1, 3, 4, 1, and 2. This is my stochastic gradient descent update. And I'll keep repeating the whole process again and again. By the way, if you noticed, and I also emphasized that when I was calculating the gradient, by applying the chain rule, you see we went from the rightmost side, the output side, which is where you're incurring the loss, slowly to the left side, which is why this is known as backpropagation. So that was forward pass. All these calculations are part of what is known as backpropagation. And that's essentially your deep neural network. And I've shown you an illustration of that when the network is not very deep and the calculations are simple. Now, before I show you the Python implementation, let me also make a comment. If in case there were H hidden neurons or neurons in the hidden layer, you will start getting vectors in these terms, and these will appear with transposes. And if you had that many hidden layers, you will get some other terms as vectors. So instead of single variable calculus, you will have to rely on vector calculus, multivariate calculus, which is something that you've just been introduced to for most of you in this course. So I will not do that today, but you can imagine how the single variable calculations will now slowly spread their wings in the full avatar of multivariate calculus. Okay? सब तो सो गए मेरी कहानी सुन के, तो मैं आपको थोड़ा पाइथन दिखाता हूँ. Let's see. Can you guys see? Now? No? Now? Okay. Now? It might take a little time. I'm just creating the data here. The data is being created just like last time. Some normalization. See, I've taken, well, actually, you know what? I've done the calculations for 1 hidden neuron. Let's do it for 10 hidden neurons. Learning rate, epochs. I initialize my weight. I define the sigmoid function, the derivative of the sigmoid function, compute the loss. This is your main stochastic gradient update that's happening. These are your gradients that are computed. This is the stochastic gradient update, line numbers 80 to 84. Then everything is kept in history. And let's play this. It will take a little while, and then I can show you the animation. So this is the final instance. Let me show you. So here, the curve of, the curve of best fit began with random weights, and because we're using a sigmoid function, this is the shape of the sigmoid output. That's the curve, right? And slowly it adjusts itself. This is with 10 neurons in the hidden layer. You see very quickly it more or less starts approximating the data. I also have, well, I have to run this because I overwrote the file. So let's run this again. Give it a couple of minutes. This is with 1 neuron in the hidden layer, the calculation that I did on the board. All right, that's the final output. Let me play the animation. And you can tell me what is the difference that you notice. Okay, this was the initial position, turned out to be off somewhere. You have the loss value. Do you notice any difference between this case and the case where we use 10 neurons in the hidden layer? What is the difference? It took more time to get closer to the data. If you have more neurons, it gets there faster. Faster in terms of the epochs. Right? And how many neurons is the human body made of? Must have learned this in your nature's machine class now. They don't talk about neurons? They do? Oh, and they must have told you how many neurons approximately does the human body have, the human nervous system, or the mammalian nervous system. Forgotten or not told? Forgotten? Okay. Your homework is to find that out and tell me in the next class. All right? Also, it does fairly well, but it never really gets as good as, to become as good as the case that I showed earlier. All right? Okay, so that's all I have for today. Hopefully, this has given you some flavor of this very new age technology, which is at the forefront of most AI ML algorithms, the deep neural network, and the calculus, the mechanics of the math behind all that super hi-fi technology. Okay, now your job is to play with the code that I will upload and get a better feel for what's going on, and see if you're able to repeat this with different activation function. Instead of the sigmoid activation function, try a different activation function. Try ReLU or Google different types of activation functions and see what difference do you notice. All right? Thank you so much. Bye.